second tutorial by Tanja, Professor Tanja Lange. So I don't know whether there is anyone who doesn't know her, but probably there is no one here who attended 7 Indocrypts successive. And so here is Tanja from 2005, I should say. She's come into Indocrypt, and she served as program chair. She gave invited talks, she presented papers, I think, and only thing was left for her to give a tutorial, which she is going to give today. And again, the cycle will start, I guess. So,
yeah. So it's my pleasure to thank the organizers for inviting me. I was not quite seeing it as a collection of Indocrypts and tutorial invited speakers that I have to like collect them all. But I'm very happy to be back to India. I really like being here, and so thanks a lot for inviting me.
and the spicy vegetarian food?
Yes, and the spicy food and the ease for vegetarian food is much appreciated. So the topic of the tutorial was elliptic curves for applications. Part of this is joint work with Dan Bernstein, quite a large part, and then I also promised to talk about a recent cryptography library, which is also part with my former PhD student Peter Schwabe, who is now a postdoc at the Academia Sinica in Taiwan. Before I start with explaining to you what an elliptic curve is, let me give you some motivation why we want to use ECC. Almost 2 years ago, there was a big announcement by a team in Lausanne, but many more, there was also France and Japan involved, that they had factored the next RSA challenge. A 768-bit modulus was successfully factored, and they stated that this took 2 years of computations on a quite large cluster of about 1,000 CPUs, and the estimate of how long it would take to factor 1024-bit RSA would be about 1,000 times harder. Now, when you look on what's available, if you look online, there's the same Electronic Frontier Foundation that Roger mentioned in his talk. They have an SSL observatory. So they crawl the web and they look at all the certificates that are out there. And more than 50% of all certificates are 1024-bit RSA. And now I understand what the computer was trying to tell me, that not all fonts show. What it says here is less than or equal to 1024. So we'll have an interesting time spotting the math mistakes. The slides will be online, including all the symbols. And so there are some certificates which have far less than 1,000, but there are even some 512-bit certificates. So an academic team can factor a 768-bit modulus, and you still find in the wild certificates with 512 bits or significantly less than 1024. And 50% of them are no harder than, well, 1,000 times harder than what an academic team can do. So if you want this, like the one I'm presenting from, usually has 2 cores nowadays. Sure, if you have a notebook, then it's a lighter processor, but a standard laptop has 2 cores. But if you take a GPU, a graphics card that many people buy for gaming or for enhanced processing of images, that thing has 60 cores in one thing. And my computers can take 2 of those cards. Then the EPFL team that was leading the factorization effort, they have a cluster of 200 PlayStations. Each of those PlayStations makes 6 cores available to the implementer. So they have, just by themselves, 1,200 cores, which is more than the 1,000 CPU cores that were mentioned up here. Going further, we've been doing a big computation. For part of that, Dan got access to one of the big clusters in the US, the TACC Ranger supercomputer. That thing alone has more than 60,000 cores. So suddenly the 1,000 times 1,000 for a year doesn't look that big. I mean, this is just one of the supercomputers. It's certainly not the only supercomputer. I mean, I have access to one in the Netherlands. He has access to some more in the US. So you pull your people together. And then, well, defending against the good guys is easy, similar to Tor. I mean, we're just academics. You see what resources we have. What you don't see is how many resources the bad guys have. If they want to factor an RSA modulus, well, they start by getting a botnet, So they get lots of free computation time. And estimates are that the botnet configure controls about 10 million cores. So if you have that at your disposal, even if you don't run all of them full time, factoring 1024-bit RSA is not that hard. It's not out of reach in any case. So in perspective of this, 2003 Shamir, the S in RSA, said, well, you should move away from 1000-bit RSA. Go to something larger. So he was estimating if somebody, instead of using normal off-the-shelf CPUs, somebody would build a customized ASIC design and use that to factor, then it would take, for a year, factoring 1000-bit modulus, he could do this for about 10 million US dollars. That's more than I have, of course, but it's nothing, I mean, it's easy on a, say, defense budget. People could do that. Now, with hardware design, it's never clear whether they take into account the costs of the designer. In this case, they didn't, but just the hardware for 10 million and then add some PhD student who does this for his project. Also, the RSA company then quickly said, yeah, well, move to something larger. And then NIST, the National Institute for Standards and Technology in the US, also advised people to go to larger moduli. So starting 2010, people should shift away from 1000-bit RSA to at least 2000, preferably 3000. These recommendations don't even take into account that you might have more powerful algorithms. They only take the normal factorization algorithms into account. But if you're an attacker and you say, well, I've got several keys that I would like to break, you can actually reduce the cost per key by using so-called batching algorithms. So if you want to attack many, then the costs per key goes down. So the general estimate is that for a 1000-bit key, it takes about 2 to the 80 operations. For a 2000-bit, it's about 112. And if you bring batching into the picture, you can go down to something like 92, 2 to the 92 for one 2000-bit RSA key. So if you look at what this comes from, RSA has this public modulus, which is a product of 2 primes. So if you see a 1000-bit modulus, then you know it comes from 2 primes, which have both about 500 bits. There's quite a few of those. There's 2 to the 503 different primes up to 512 bits. So, of course, if you want to enumerate them, or if you just want to check, does this prime divide the modulus? That's a huge computation, but that's not how the factorization algorithms work. The best factorization algorithms we know use 2 to the 80, about 2 to the 80 bit operations to break this. If you have 2000 bit, yeah, I already mentioned the 112, and then a now comfortable security level of 128, 2 to the 128 bit operations, that requires you to upgrade to a modulus which has 3000 bits. So there's lots of primes to choose from, but the attacks are much faster than that. So what brings down the cost from the attacks is a thing called, well, index calculus, or finding congruences and combining them with a big matrix step. This was already known to some extent when RSA was proposed. There was a CFRAC algorithm, and the linear sieve came very quickly. But it wasn't until the quadratic sieve, and then in 1990, the number field sieve, that the time to factor RSA modulus went down to really sub-exponential and noticeably sub-exponential, like something on the scale of 2 to the log n to the 1/3. So if you look at what this means for the different algorithms, so the initial algorithms, So CFRAC, the algorithm which was already out, would have predicted that a 1000-bit modulus takes 2 to the 120. That's a security level which is still very comfortable nowadays. So if that was the best algorithm, then we would still stick with 1000-bit RSA. And the scaling, if you double your modulus, it would also significantly increase the cost for breaking that one. If you then look at the improvements, so the linear sieve, the quadratic sieve, and the number-filled sieve, this is now the 2 to the 80 that we have as a common estimate of the hardness of breaking RSA 1024. The difference between the numbers, here it was 50 in the exponents, here's still 50. still 50. But now it's going down. So the gap narrows. If you double your key size, the gain in security has gotten smaller. And dealing with 2000-bit moduli is not pleasant. If you're doing smart card implementations, you suffer from this. Even if you're doing a laptop implementation, if you have, say, a notebook with some atom processors, you will feel that it costs you much more time to use 2000-bit moduli than 1000-bit moduli. A student of mine came to me and said, well, he's unhappy with using HTTPS. He's, well, a security student, so he wants a 4000-bit modulus. And he really is unhappy with the connection time he sees. He sees several seconds, whereas otherwise it would be instantaneous. So looking at the history, RSA has been around for longer than ECC. RSA is from 1977, ECC is from 1985. But in the initial paper that Miller published, the crypto paper of his, has actually quite a few attacks. So he's saying, well, I'm proposing elliptic curves as a basis for cryptography, and here's all the attacks I went through, here's all the things I excluded. All of these don't give you any sub-exponential attacks. There have been few improvements. I mean, we're running a conference on elliptic curve cryptography every year, and every year we have some talks on attacks. But most of these attacks are more confirming that breaking elliptic curves is hard, rather than having a breakthrough thing. There are some which are weak. There's entire classes of curves that are easily breakable, but if you do a good choice of elliptic curves, then there's essentially no loss in security from 85 till now. Whereas for RSA, well, you see here quite an improvement in different factorization algorithms. And the biggest loss in security was the number-filled CIF in 1990. Since then, it's been pretty stable, similar story to elliptic curves, just at a much lower level of security. So comparing to 3000-bit RSA, if you would do the same with elliptic curve, whatever this is, elliptic curves would have a much smaller modulus. It would be a field or a prime of just 256 bits to offer comparable security. At that level, elliptic curves are much faster. So in 2000, it was still worth a research paper to discuss whether elliptic curves could beat the speed of RSA. Once you reach 1000-bit RSA, and that corresponds to, well, 160-bit elliptic curves, then already elliptic curves are faster, and the gap widens a lot. So RSA gets much, much slower with an increased security. Elliptic curves get just somewhat slower. So arithmetic is linear in the bit length, and, well, there's quite a gap between those. So this also has some influence on standards. So NIST is now proposing most elliptic curves. The US government is recommending to move away from RSA for government communication. So their latest recommendations of algorithms only contains elliptic curves. So this is the Suite B algorithms. That's all elliptic curves. Also, if you look at what's in your passports, if you have an electronic passport which does signatures, then chances are pretty good it's an elliptic curve. I know that for Germany, there is an elliptic curve in the electronic passports, just because it's much more suitable for small devices and has a better security history. And then, yeah, Roger already mentioned that some people like improving things like TCP. So Dan Bernstein, who is your program chair together with Sanjit this year, has a proposal out for curve CP, which is a replacement for TCP, and this curve in there stands for elliptic curves. And he also has DNS curve, similarly doing a secure version of the domain name service with using elliptic curves. So if you browse the internet, right now it's mostly RSA, but elliptic curves are getting more and more common. So I hope this motivates you enough to find out what elliptic curves are. Before we get to this, let's do a little warm-up. I mean, we all, before primary school, learned how to read the clock. Like, this used to have X's and Y's. It has on my computer. Not quite sure how to repair this. This looks pretty bad. I mean, it's worse than just the X and Y's missing. It also misses all the graphics.
Better to use your own laptop.
I could use my laptop. Is this one connected or?
I exported to PDF.
This is PDF. This is PDF produced from Tech.
This is not harder.
No, this is somebody else's laptop. So I'll tell you a few things that I can say already while the picture is not properly showing. My laptop takes a little while to boot. Okay, so an elliptic curve is some shape which is not, so when I give this talk to companies, I explain to them, yes, I'm going to show you a circle, but it doesn't mean that I'm talking about ellipses. So an elliptic curve is not the same as an ellipse. But showing you the circle first gives us a little bit of a warm-up. So once we have the real picture here, it will show you the circle equation, so it has x squared plus y squared equals 1. So what I'm talking about here is the unit circle, and x is going this direction, and y is going that direction. Now, when you learned the clock, it was because your parents wanted to tell you, it's now 2 o'clock, be back from playing at 3 o'clock. So you learned how to add 1 hour, or I'll be back in 3 hours, so you learn how to add 3 hours. So we're very familiar with how to add numbers on the clock. We usually don't say we add 2 o'clock plus 5 o'clock, but if I would choose this as a weird way of speaking, you would understand I just want to add 2 plus 5 is 7. And at some point, well, I wrap around more 12. So then I have this modular operation, or I can say, well, I'm looking at the pieces of a cake, and I'm putting this piece of a cake which corresponds to 2 o'clock and the 5 o'clock piece together, then I get a 7 o'clock piece. And so I will define an addition which is doing exactly that. So we will define an addition on this curve, which is not an elliptic curve, because later on we'll do addition on an elliptic curve. Magic, there is x and y's, and so we now have a curve. Nice. So what I was talking about is we have lots of points on this curve. So we have all the times that you know on a clock. So for instance, we have the 12 o'clock point up there, which has x value of 0, y value of 1. We have the 6 o'clock point down here at 0, minus 1, 3 o'clock, then 9 o'clock. Now, this thing is, y is about half, and then go over to here, so that will be 2 o'clock, yeah. Mine is still showing. Yes, so now the guess was 7 o'clock, and yes, indeed, there we are, 7 o'clock. Continuing this way, so I can write down 130, which is square root of 2, square root of 1 over 2, square root of 1 over 2. And I can also find lots of points which don't have nice times. So just saying, well, this is a Pythagorean triple, 3, 4, 5, so this is a point on the curve. And then for any point on the curve, I can change plus and minus of the x-coordinate, I change plus and minus of the y-coordinate. I can also swap the x and the y-coordinate. I mean, if I have a point here, I also have a corresponding point up there. So once I found one point, I find many more points just playing with those coordinates, and that was just one example. So just take your favorite Pythagorean triple, and you find more points. Now, to explain the addition that I was telling you in formulas, so I said, well, we add 2 o'clock and 5 o'clock, so we get 7 o'clock, or we put those pieces of pizza or pieces of cake together. I'm defining the sum of P1 and P2 to be the point where it's alpha 1 plus alpha 2. So you take the P2 and put alpha 2 on top of it. So if you write this with sine and cosine, the alpha is this angle, so the x-coordinate, that's this direction, that's the sine of alpha 1, and the y-coordinate is the cosine of alpha 1. Now, for the trigonometric laws, you found these addition laws. So if I add alpha 1 plus alpha 2 and want to express this in terms of sine of alpha 1, cosine alpha 1, and the same as alpha 2, then here are the rules for that. So the sine of alpha 1 plus alpha 2, I can write as the sine of alpha 1 times cosine alpha 2 plus the cosine alpha 1 sine alpha 2. And similarly, for the cosine of alpha 1 plus alpha 2, there's a similar rule, which is again expressed in the input values. So this way, I can define an addition on the clock. So adding 2 points is just adding the angles. So, well, if I take 2 numbers, I add them, then this is just a normal rule of adding numbers. If I add 0, so if I take the point up here, which I call the neutral element, if I add 0 degrees or 360 degrees, I don't change the value. So this is just a kind of different representation of additions of numbers modulo 360. So obviously this is the group. I can add 2 things. I can subtract 1 from the other. Everything is nicely defined. So the negative of a point is taking the same, well, first of all, taking minus alpha. So if this is alpha, then minus alpha is over here. So it has the same x-coordinate, it has the same y-coordinate, but the x-coordinate changes the sign. Now, I don't want to teach my computer about trigonometric formulas. I want to have a point represented as x and y and add 2 points in this representation. So I'm now kicking all of the sines and cosines, and what I get is, well, this was the sine of alpha 1, cosine alpha 2, cosine alpha 1, sine alpha 2. So I can nicely express it in the input coordinates, and similarly for the y-coordinate. So I now have, in terms of the coordinates of the point, removed the alphas and replaced them with x and y coordinates. Gives me exactly the same information. Okay, so if I now add a point with the same y-coordinate and the negative of the x-coordinate, I get the 12 o'clock point. And if I now define a scalar multiplication, I take a point and add it to itself k times, just adding the alpha to itself k times, or using these formulas, I take p plus p plus p and so on, until I summed up p copies of this point, k copies of this point. So we all know that 2 o'clock plus 5 o'clock should give 7 o'clock, but now let's see that this also works in the formulas. So the 2 o'clock point, that was the square root of 3/4, comma 1/2, and the 5 o'clock point was the 1/2 plus square root of minus square root of 3/4. So when you add those two, then we take the x1, so that's the this value times y2, so we get minus 3/4 plus the y value of this one, so plus 1/4, that is minus 3/4 plus 1/4, so it's minus 1/2. And similarly for the other coordinate, we have the y coordinates, the product thereof minus the other two, so then we have 2 times 1/2 of 3/4, so we get exactly this value, so 7 o'clock. Similarly, adding other points works the same way. Also taking this weird point, the 3/5, 4/5 point, adding it to itself gives something 24 over 25, comma 7 over 25. Now I can add it 3 times to itself. That gives 117 over 125, minus 44 over 125. Continuing like this, so here we notice the denominator is always, well, if I have 2 times the point, then it's 5 squared. Here it's 3 times the point, it's 5 cubed. Here it's 4 times the point, so it's 5 to the power of 4. So if I would show you these numbers and suggest, hey, use this as a Diffie-Hellman key exchange, you would have a very easy time breaking the discrete log problem by just looking at what the denominators are. So we're not going to use the clock as such for cryptography. But let me first stick to this example. Just it's nicer to draw numbers over the reals than to draw numbers over the fine fields. But we come to that. So if I add the 12 o'clock point, well, it shouldn't change anything from the explanation with the alphas. And in fact, yes, if we have y2 is 1, then we get exactly x1 here. And x2 is 0, so this term disappears. And here we have y1 times 1 minus x1 times 0. So that gives us x1 comma y1. Also, if we take a point here and the point on the other side with these formulas, then here we have x1 minus y1, x1 y1, and here we have y1 minus x1. So this term gives 0. And here we have y1 squared minus x1 squared. That's the only part we have to watch out. So we have x squared plus y squared, but this is a point on the curve. So it satisfies this formula. So the result is 0, 1. So the negative of a point xy is minus x, y. Now, trying to avoid this easy discrete log attack that I just mentioned with the powers of 5, here is the same clock over f7. So I take all the numbers, mod 7. I'm drawing them so that 0 is in the middle, then it's plus 1, minus 1, or plus 2. So you see all the points here. So I represent f7 symmetrically around 0. And all the operations now take place mod 7. Well, it's a group law before, so it will stay being a group law once you compute mod 7. Now, doing this with a bit bigger numbers, for 7, I assume that you're all able to look at those points and tell me exactly what the discrete log of this point based off this point is. But once I give you a big fine field, like this one here, and I give you this point, the numbers grow for a little while just because this is much smaller than the modulus, but then the reduction kicks in. So starting here, you have a hard time figuring out what number I put in there. Now, I can tell you that I did 30 additions and reached this point. N has 6 digits. Now, if you use your computer, you should be able, either brute force search or Paul Drove, you know that one, to quickly break it, but it's not that weak anymore. It's not the obvious thing you see a power of 5 and you read off the power. So if you want to use clock cryptography, you would standardize some point, you would standardize some prime, and you would use this as a base point. And then you do a Diffie-Hellman key exchange. So Alice chooses some secret A, Bob chooses some secret B. And then Alice computes A times this published base point, Bob computes B times this published base point. And then both of them can compute the same point by Alice taking Bob's value A times and Bob taking Alice's value B times, so they both get AB times the base point. So now the two of them share a point on the curve. If you see this conversation, what you see is, well, the base point, A times the base point, and B times the base point. Depending on the security of the clock, which I'll comment on in a moment, it's hard for an attacker to find this value. So this is now a shared value that the attacker shouldn't know, and as soon as you have a shared value, you can use this, for instance, using AES and use it as your secret key, or do some key derivation function based on it. So here's a flow chart of this. What Alice computes, she picks a random A. This is just purely on her side. This is invisible to the attacker. This side is invisible to the attacker. This is their private computations. The attacker only sees this bit of communication. So the attacker only sees A times the point and B times the point, and would like to compute this shared secret key. Now, I mentioned already clocks are not elliptic curves, so what I said before about the security of elliptic curves does unfortunately not apply to the clock group. The clock group is similar in strength to RSA. Well, the modulus that I bring in can be half the size. So if you want to match the security of 2000-bit RSA, your P only needs to have 1000-bit. But that's still no great security. So it's still a sub-exponential security. So if you compare with RSA, it's half of the bit size that you get from the security. Now, let's tweak this circle a little bit. Let's take our circle and squish in the points. So I'm pushing in here, pushing in there, pushing in there. I get something which is like a starfish. So this is what I get if I add an extra term. I'm not asking for x squared plus y squared equals 1. I'm adding some extra term here. I'm saying, nah, I want to go a little bit off. Now, at the corner points, one of those coordinates is 0. So the corner points are still at the same points as on the circle. The minus 30 x squared y squared doesn't change anything if x or y equals 0. But if you come into this range, it is smaller numbers than on the circle. If I would choose a different value here, say a positive number, the curve shape would change in the other direction away from a circle. So then you would have some kind of overgrown circle and also some points on the side. But this one is easy to draw because all points fit on the slide. There is no points missing. So this curve is called an Edwards curve. And Edwards curves are an example of elliptic curves. So an Edwards curve is you take a circle and you tweak it a little bit. You add some extra factor here, some general plus d x squared y squared. And now we define an addition of these points where we take the same numerators as on the circle. We have the same x1, y2 plus y1, x2. And we have the same y1, y2 minus x1, x2. Now this was the addition on the circle. You wouldn't quite get the point on the Edwards curve. So when you divide by this factor for the x-coordinate and by this factor for the y-coordinate, then you land on the circle. So if instead of minus 30 you would write 0, it all simplifies to the circle addition law. But we want to move away from the circle, so we don't choose this parameter to be 0, but for instance we choose minus 30. And then we do the same thing. We fix a point, and we can compute on this. Now here is the comparison again. So the circle has just those values. Here we divide by those factors. And no, it's not addition of the angles anymore. This one here is much narrower than that one. But that's a good thing. If you have a simple addition law, if you see this, if you would be able to read off the angle here, then you're asking for the attacks that work against the clock. So those attacks don't work against the Edwards curve. Okay, so one thing you might ask if you're, well, either a well-trained mathematician who always asks, is this well-defined, or you're a computer programmer and you have to catch exceptions, I'm dividing here. So I have to watch out that I don't divide by 0. So I have these terms, 1 plus or minus 30 of these coordinates. And if that happens to be 0, then I'm dividing by 0. So the plus value was the x-coordinate, the minus value was the y-coordinate. Now, let's first look at the corner points where y or x equal to 0. Well, in that case, this term is 0, so the result is 1. If, however, they are both non-zero, so if at one of the other points here, 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 or there, then all those points are kind of bumped in from the circle. Go back briefly. So if we are somewhere in these regions, then 30 times x squared y squared is less than 1, just by this thing being a point on the curve. Because here, this one is less than 1, so here, this must be smaller than 1. So if you take the square root, it's still less than 1. That's the case for the x1, y1 point and for the x2, y2 point. Now if I multiply those two, that's exactly what's happening here. I have the x1, y1 and the x2, y2. Then for the first one I have that it's less than 1. For the second one it's less than 1. So their product is less than 1. So if I take 1 plus or minus this value, then, well, if it's plus, then I'm adding something, moving away from 0. If it's negative, I don't subtract as much as 1. So I'm always at a positive value. So if I'm doing this calculation over the reals, I will never, ever have a 0 divisor. OK, so if I do the calculation on the Edwards curve, here's the addition formulas again. So it's, well, trust me, no. Sit down, use your algebra system, and prove that this point is on the curve. This is the only part of the proof which is a bit nastier. I don't want to write it out. It would cost more than a slide. But your computer will easily verify for you that x3, y3 is on the curve if x1, y1 and x2, y2 were on the curve. So also associativity is a lengthy proof, but you can easily convince yourself by looking at your computer that it works. Other parts are nice. You can see, well, the negative of a point is exactly the same as on the clock. So if you have a point, x, y, then the negative is minus x, y. Well, that's because here, this part on the curve, is, on the circle is already 0, so it stays 0. This one on the circle would be 1, but that came from the addition law, namely of the x squared plus y squared equals 1. Now x squared plus y squared is 1 plus 30x squared y squared, which is what we're dividing by. So also here, same as on the circle, the 12 o'clock point is a neutral element. The negative of this point is over there. Now, in general, when you do crypto, you want to do something discrete. You don't want to have infinitely large groups. You don't want to have a certain growth of the functions. You've seen that on the circle was a bad idea to compute over the reals or rationals because the numbers grew bigger as you have an increasing number, increasing k. Similarly here also you would give away the information unless you work modulus some number. So in general, if you have an odd prime power q, for most of the examples we'll just do primes. So you take a finite field fq and you define your Edwards curve, x squared plus y squared equals 1 plus dx squared y squared, then that is a nice object for cryptography. It becomes even nicer if you insist that this d here is not a square. So if you're in a finite field, then of your q minus 1 non-zero elements, half of them are squares, half of them are non-squares. So it's not much of a restriction to insist on this not being a square. And we'll use this condition of d being a non-square to show that also here the denominators don't vanish. So if I want to show the same thing that I just proved over the reals, I was using something like something is larger than 0. In a finite field, when I compute mod p, I don't have this notion as larger than 0. So I have to get a different idea for the proof. So I'm starting with 2 points on the curve, and I want to show that the denominators don't vanish. Now, the denominators in general are this 1 plus dx1, x2, y1, y2, and here the same with a minus. So in the example before, we had d equals minus 30. So we saw a minus 30 here, and we saw a plus 30 here. In general, it's a d. The same d is up there. Now, one of the denominators would be 0 if this expression would be plus or minus 1. So let's assume it's plus or minus 1 and do some calculation, which, well, the only motivation for it is it works. And we'll find out, yes, those don't vanish. So here we go. If we take this expression, now that's a square, that's also a square, this is not a square. If you multiply squares with each other, it obviously stays a square. If you multiply a non-square with it, it becomes a non-square. So what I'm writing here is something which should not be a square. And I'm out for a contradiction showing that this would be a square. So I will contradict that D is a non-square. Okay, first thing is I just use the binomial theorem, expand this equation here. Then I resort it a little bit. And I use that these points, this point is on the curve. So x squared y squared is the same as 1 plus dx squared y squared. So I replace this part by this part. And I'm slowly growing here my x1, y1, x2, y2 with 2d's. So I'll have exactly the square of this one here. And then I have some extra terms. So expand the equation. Here, this is the square of that thing. And then just cross multiplied. And now I know, I'm assuming it's plus or minus 1, so the square of it is plus 1. This I copy. And here I also have a d x1, y1, x2, y2 times another x1, y2. So if this expression is plus or minus 1, then this thing is plus or minus 2 times x1, y1. Okay, now this thing here is the right-hand side of that equation. So I can replace it with the left-hand side. And now you see that I get a square. So whether this is plus or minus 1, I can use the binomial theorem and get x1 plus or minus y1 squared. So at this point I want to shout, yes, I have a non-square equals a square, and so I'm done, right? Okay, I have to do slight case distinction. It might happen that some values are 0. So let's first assume that this value here is non-zero. Yes, then I do get what I was hoping for. I can divide by this whole thing here, and I get D is a square. I assume D is not a square, so I get a contradiction. Now, if this happens to be 0, I have to start something else. Then I do the same proof and instead put in a minus here. So doing the same steps, if x2 minus y2 is non-zero, I'll again get a contradiction which looks like this thing, just the sign here flipped. Now, if both of them are 0, x plus y and x minus y, well, that means that both of them are 0. But the 0 point, if I'm an Edwards curve, this is not a point on the curve. So the third case doesn't exist. So we have found a contradiction. If D is not a square, then the denominator on the Edwards curve cannot vanish. So here we have found a replacement for this proof. So this addition law does not have any exception. So if you're a computer programmer, you can just take any 2 points and add them. You do not have to put if denominator equals 0, then exceptional procedure. So it's kind of neat. If you've done elliptic curves before, then you most likely have seen lots of different cases, and we can all skip those together. So to use this in a protocol, similar to the clock, I would now publish a base point, but the clock is just one group. There is no parameters. For the Edwards curve, I also have to fix a D. So I start by publishing a curve, just my choice of a non-square D. I publish a prime P, and I publish a base point. And then I do the same De-Fermat key exchange that I showed for the clock. Now, this sounds like each time Alice and Bob want to talk, both of them have to be online, have to be interacting. A much more common scenario is that one of them puts online somewhere his public key, says, well, hi, I'm a server, here is my public key, B times your point, and then if Alice wants to get some connection to the server, she uses her secret key A and does this computation. This is active from A's side, but passive from B's side. So at that moment, then A can encrypt something to B, having computed this shared key. So then A can talk to the server, can send something on, and knows that the server will be able to read it. Adding a little bit more, well, you might be worried that this is too static. It's always the same A, it's always the same B. So they add in some nonces, they add some unique values for each communication, and then, of course, they have to send along this nonce. So from there on, there's the public key. Alice says, hi, I'm Alice, my key is A times XY. I'm talking to you, so then the server can pull out of the drawer its B and can compute the same value, will use the same nonce that's provided, and then use some symmetric cryptography to compute an authentication and encryption. So we don't need the server to be online all the time. You can send something to the server, and then the server wakes up and can reply. Oh, sorry. So when the server receives this package, then the server can compute it and can use it, and, well, adding authentication. So at the end of this tutorial, Dan will go on stage and show what we actually are doing in the SALT library, and it's basically this thing, just more details filled in. Okay, so this is a pre-advertisement, so there will be something on the SALT library. If you're already bored with Edwards curves and have a laptop in front of you, you can go to this webpage, saltcaseproject.eu. We have a mirror up on cr.yp.to, but this is still the official case. It is a nice and fast library that we'll show you some more details on. If you are curious what the math is behind, then stay tuned. So our impression is that that is, well, very secure, so we shows security level of 128 bits, and we shows good implementations for that. Despite all the security, the speed is pretty good. So if you're a server, then chances are that your network bandwidth is more limited than your computational power. So if you've just a normal Core 2 quad processor, you can handle that many, well, 100,000 new clients, 100,000 key exchanges in 40 seconds of computation. If you look, that's like a megabit internet connection. So if you have a very good internet connection, then you might reach the levels of the limits of this, but for essentially normal users, that's faster than your internet is. And most of the time, you don't get only new clients. Most of the time, you have clients who come back. So brief summary, Edwards curves are pretty cool. OK, so what do Edwards curves have to offer to you? How do we compute this thing? I said before, you take the point and add it to itself k times. So we would have k minus 1 additions. That's surely not the best we can do. What we usually do is we take the binary representation. So we take this number a here, say 23, write it in binary as 16 plus 4 is 20, plus 2 is 22, plus 1 is 23, and then use this binary representation reading from the most significant bit and doing this chain of doublings and additions. Whenever, so we start here, whenever we see 1, we add p, and then we double, then we add p again, then we double, then we add p again. So the first things is just 2 doublings in a row because there's the coefficient 0, and then it's plus p, double, plus p, double, plus p. In general, if you have a scalar of this length where the first bit is a 1, then here is the recursive formula. It's, well, n doublings, and here's all the additions depending on what the bit is. We'll see some more efficient methods later in this tutorial, but this already tells you it's not k doublings, it's log of k doublings. This also means what we have to focus on are additions and doublings. Actually, for each bit, we'll do 1 doubling, and with chance 1/2, we'll do an addition. So if you want to have faster group operations, here is another set. So this is not exactly the same formula that I showed you before. Well, sorry, this I'm getting ahead of myself. So this is the formulas I showed you before, but if you would want to implement this, and they talk to the hardware people, or even on a PC, then you see you have to do 2 inversions per group operations. And an inversion is much, much more expensive than a multiplication. Now, if you're a person doing hand calculation and you're working with fractions, you're perfectly fine adding and multiplying fractions. You have your numerator grow and the denominator grow. There's actually no need to compute the result. And the same is true mod p. You can compute with fractions. You don't have to evaluate the division by something. So we'll now keep points by this representation. So we take y with some denominator, x with some denominator, and I would like to have both denominators be the same. I can just cross-multiply them. So that means I'm changing the 2-coordinate representation to a 3-coordinate representation. Needs somewhat more space, but I can save all the inversions. Well, or rather, I postpone all of them, and at the very end, I do one big inversion. Okay, so what happens to the formula is the following. I now have to deal with the z-coordinates. That comes in here. So well, it doesn't come totally for free, but most of these operations, the x1, y, x1, the y1, y2, these are the same operation that we would do anyway. I was highlighting this one here in blue. So this doesn't look like any of the operations you would see normally. But if we expand this, cross-multiply, remove the c and the d, then you see that is the numerator of the x-coordinate. But if you would compute it from scratch, you would have one multiplication here and one multiplication there, and we save one multiplication in this operation. So with a little bit of tweaking things, this is how you can compute one addition without inversions. So it takes 1 squaring, that's in the b value, 10 multiplication, and 1 multiplication by d. So m sub d means we multiply by the curve parameter. That was happening up here. Now, if you double a point, and I showed you for each bit of your scalar you have one doubling, then we can simplify the formulas a bit further. Now, both points have the same coordinates. So if we take this thing and just have the x1, y1, x1, y1, okay, that's obviously 2 times xy. But even nicer here, this guy, 1 plus dx squared y squared. That is the right-hand side of the curve equation. Okay, if it's the right-hand side of the curve equation, we can replace it by the left-hand side of the curve equation, here. So instead of writing this side, we write that side. And now suddenly the degree of this formula is just 2. Up here is something of degree 2 plus 2. So the degree dropped from 4 down to 2. Each extra degree costs an extra multiplication, so this thing does help in speeding up the computation. Now for the y-coordinate, well, that's obviously y squared minus x squared, no magic here. Here I'm again using the curve equation. I'm replacing this expression by x squared plus y squared minus 1. I get a 2 here and minus this representation. Doing the same without inversions gives me these formulas. And yes, doublings are much faster than additions. Additions were 10 multiplications and 1 squaring essentially, and the doublings now have just 4 squarings and 3 multiplications. So the more frequent operation is cheaper. Now, we'll see later that I can even reduce the number of additions by using a different representation, so having a speed up in they can be somewhat faster for addition. But it's kind of funny to see that these formulas are totally independent of the curve parameter d. The other ones had the 1 plus or minus d x squared y squared in there, and here there's no more d. You can also increase the set of curves that we're dealing with to go for Edwards curves, to twisted Edwards curves, by changing the little parameter here. So usually we just have x squared y squared equals 1 plus dx squared y squared, and we now put in the parameter a there. When we defined twisted Edwards curve, our main motivation was to just cover more curves, but we then learned that even, so it's not just getting more curves, you can also get a faster arithmetic. So for the special choice of a being -1, the cost of an addition drops from 10 multiplications plus 1 squaring down to 8 multiplications, which is related to using these formulas, so it doesn't give you that it also works for doubling, so you still have to watch out, but it's still quite an improvement in speed. Okay, so now we could use the system to sign a message. ECDSA is a standardized algorithm. The E usually stands for elliptic curves, not for Edwards curves. So what I'm showing you here is not exactly the real ECDSA, but on the protocol level, it's the same. You take a curve, you take a point on the curve, and if you replace an Edwards curve by a Weierstrass curve, which we'll see in a moment, then that's exactly what's standardized. So here, we take a point on the curve, modulus some prime. We also need one extra parameter called the order of the point. So if you have a finite field, and you look at all the solutions x and y that satisfy such a curve equation, then you have only q choices for x, you have only q choices for y, and not all of them are going to work. About a total of q points are on this curve. So if you take a point and add it to itself repeatedly, at some point you'll be back. Or at some point you even, just before being back, you hit the neutral element. The smallest integer such that L times P gives this neutral element, that is called the order of the point. So for this system, we also need to know what the order of the point is. So we'll publish the curve and we publish the order of the point. Then the signature scheme works the same way as public key system. You have your public key, which is A times P, so Alice publishes A times P, and she has the secret key, little a. We also need a hash function, so if you have a long message, we somehow have to break it down to something which is as short as the message itself, as the modulus. So we use some hash functions with output lengths about the group order in bits. And then what Alice does to say, yes, I hereby sign this document, is she hashes the document, so she computes h of m, and then let's see what the other parts are. She takes a random value k, computes k times p. Of that thing, she takes the y coordinate, let's call it little r, put it in here, and then A was her secret key. Well, it's a signature scheme, so she has to prove that she knows her secret. That's why the little a appears in here. And then take the same k that she had before, invert it, modulo the order of p, and compute this product. Then her signature on the message m is r, s. So to say, yes, I authorize this message, she publishes the message and r and s. Now, if somebody wants to validate that the signature is correct, wants to verify it, then what this person computes is he takes the part S here and computes S inverse. And there's two parts. She computes S inverse times the hash of the message and S inverse times this value R, this first part of the signature. Then there's a big computation. That person looks up the public key of Alice, computes this W2 times the public key of Alice, this W1 times the base point, computes this point, the x and y coordinate, and then looks at the x coordinate of this and checks whether it's equal to R, this thing here, modulo L. Now, if Alice was really signing this document, why does it work? So what the verification is, W1P and W2PA. So for W1, that was S inverse times the hash of the message, and this was S inverse times R. Now PA, up here, that's Alice's public key. So that's A times P. So what we have here is RA, and what we have here is H of M, and both of them are multiplied by S inverse. Looking back to the definition of S, as K inverse times exactly the same sum here, that means we have the S inverse, so we're left with K itself. So we're computing K times P. Alice's first step was to compute K times P. The definition of R was take K times P, look at the Y coordinate, and compute it mod L. So if Alice did sign this properly, then the Y coordinate of this value should equal R. And if somebody does not know A, then this person shouldn't be able to do this. So the attacker, the whole secret in this is in the little a. The attacker can do everything else. The attacker can hash, the attacker can take a random K. So R somehow feels like it doesn't contain any secret. Anybody can pick some K and compute little r. So if the attacker wants to break the scheme, wants to do the same computation as Alice does, then it feels like the attacker has to compute little a here given just PA. So that would be breaking the discrete log system, and that's a problem which is well understood on elliptic curves. That's where all the security estimates come from when I say, well, use a curve with 256 bits, you get 128-bit security. That's because breaking the discrete log system takes about square root of the group order. However, there are some cases where breaking signatures was easy. Now, I said anybody can do the part of picking some R and computing it. So you might feel like, well, once I've used the K, I can publish it. You can just say, yes, I did do this computation, here's my K. Now, if you ever publish K, then bad things happen. If you have a message and this R, S, then remembering how S was defined, now the only unknown value in the S equal to K inverse H of M plus R times A, the only unknown thing is A. So you can rewrite the equation to be A, the secret, now no more secret, being congruent to SK minus H of M divided by R. So as soon as somebody publishes a K, this one-time secret does give you the value of the long-term secret. So never ever tell anybody which K you used. However, there's a second lesson. Don't reuse randomness. Something which, well, I was mentioning in my classes in passing, but never really bothered much with it. Until last year at the Case Computer Club in December, there was a very nice talk about the failure of the PlayStation 3 system. So on stage were a group of hackers who were celebrating all the different ways that the PlayStation could be broken. So PlayStation is this, well, I mentioned it before in the context with Lausanne. They have 200 PlayStations, so for them, the PlayStation is a powerful computer. There are some people who think that it's something used for gaming. Maybe even the majority of the users thinks it's something for gaming. But the PlayStation, well, Sony was getting some users by promising that the PlayStation would be usable as a computer and as a gaming platform. So they had this dual operating system, one which was running the PlayStation games and one which you could do, well, powerful computations. And then one nice day, Sony decided that actually, we're not getting much revenue from selling those games. Those bastard people use them as a cluster. They buy 200 of them and put them somewhere in a cellar, and we never ever see a penny from them buying our games. Or even worse, that people who are sharing games, or people who write their own games. And so Sony decided to do an update, which would give you much better networking experience. And we are on the side turned off this other operating system that actually nobody should use. And that got some people angry. I mean, for instance, my student bought a PlayStation for work, but also for playing. And then he couldn't upgrade the system because then it would kill this dual boot option. And then some people got sufficiently angry to hack the thing to find out what's behind it. And at some point they got to, yeah, they know all the details, but then there is this part when the PlayStation boots, it only loads systems that have a signature with Sony's secret key. And Sony was saying, haha, this is an elliptic curve signature. And I'm giving this tutorial because I'm convinced that elliptic curves are good. So I would say, well, at that point, end of the story. Now, the hacker team got a mathematician on board. Like, well, hey, try to see whether you can break maybe these elliptic curves. And what they noticed was that when you look at two signatures of two different games, or in general you look at two signatures on different messages, well, the messages were different. The second part of the signatures was different. But the first part of the signatures was the same. Now this r is k times a point, and then the y-coordinate. If the y-coordinates are the same, well, okay, you have 2 points which have the same y-coordinate, but chances are pretty good it comes from the same k. And they saw this for every signature they looked at. So what Sony was doing was invest a lot in generating a really good number, a really good random number, and then keep using it. Now, there's a little bit of a problem there. I mean, they didn't do the mistake of publishing k, but they did something which in just one step gives you k. So let's look at this. If I take the difference of the two signatures, then the RA, well, R is the same, so this part disappears. I'm left with k inverse and the difference of the hashes. And I know the hashes because I know the messages. So I can compute k as the difference of the signatures minus divided by the difference of the hashes. Now I have k, and then I go back to a previously solved problem, and I compute the secret key. So in the presentation, they were saying, yep, they now have Sony's private signing key, and they even took some homebrew game and signed it and showed that they could run it. And they were proudly advertising that they did a proper signature. They choose a fresh key. So they now have a signature which does not have the same bug. But there's more things that you could do. You could, for instance, if you have a bad random number generator, even if you keep your k secret, even if you pick a fresh k every time, if, say, always the top 5 bits are 0, then it's also possible to set up an attack. You need many more signatures, not just 2. You need, like, on the scale of 1,000. But if you have a fixed bit pattern in some bits, then 1,000 signatures are enough to reveal the secret key with some other attacks. You can also be an evil person, can be a malicious signer and say, yeah, I want to buy stock from this company. But what if the stock market is going to crash? Maybe this company is going bankrupt or something. Then I want to be able to send an email to my stockbroker saying, what, you brought me some, you bought some of this? You idiot. I said, don't buy, not buy. So if you know that at someday you want to send 2 messages, you want to send 1 message, but you want to be able to say, no, I sent this other message. So you actually want to be able to use one signature interchangeably for both messages. Now, you have to use your secret key in the message, otherwise your broker won't accept it. So you have to generate your secret key in a very particular way. So assume that you know you want to be able to sign message M1 and M2. You want to be able to swap between the two. So you compute the hash values, and you would like that the same value would work. Now, those 2 messages have very different hash values. So it must be in your secret key, this little a, that you get both messages to fit. So you take some RS, where R was the y-coordinate. Now this fits with 2 points, the plus R and the minus R. So you'll make your signature RS for the first message be with plus, and for the second message be with minus. Write out these 2 equations, and you get 1 equation for your secret key. Now, of course, the moment that you tell your broker, no, it was this other message, your broker has 2 messages from you which have matching signatures. At that moment, your broker can do the same computation as you do here and also calculate your secret. So it's a risky thing. So you should only, well, first of all, you're not malicious, right? You're a good guy. If you were malicious, you should only do this if you're fairly likely that you want to stick with M2. You just want to have an insurance, just in case you want to sign M2, want to claim it was M2, but it does cost you. You lose your secret key. Now, this is easy to avoid. I'm using here that I have R and minus R. If you just include 1 bit of X1, you avoid this attack. So this is something which is called malleability of the signature if you have a signature which also fits on a different message. Okay, so I advertised before that Edwards curves would be elliptic curves. Now those of you who have seen textbooks or talks on elliptic curves, they usually don't start with a clock. They usually start with some other pictures. They usually start with a curve of this shape. Some variable squared equals to some other variable cubed. This is already a little bit simplified because I'm only talking about odd characteristic fields. So if you have a field, say integers mod p, where p is odd, then any elliptic curve can be written in this shape. This is called a Weierstrass curve. If you would be in characteristic 2 or characteristic 3, well, characteristic 3 fits here as well, of this term. If you were in characteristic 2, then you would have some extra terms over here. So when you draw this thing, then you notice that, then you notice it's y squared, v squared, so it is symmetric. If you have one point here, you'll also find a point with v. You find a point with minus v. It doesn't have the same four-way symmetry that the Edwards curve had. With Edwards curve, you have this point, this point, this point, this point. Here, we have one variable squared, and the other one is cubed. Okay, so this side here has, well, one root or three roots. So draw the case where it has just one real root. And then we find points on this curve. And similar to before, I can define an addition. Now, for this curve shape, we have a pictorial way of describing it. If you want to see, we also have a pictorial way of describing Edwards curves, but I usually think the analogy with the clock is nice enough. So for Weierstrass curves, here's what we do. We take 2 points, P and Q, and we would like to add those 2 points. So you want to define P plus Q. The first step is we draw a line between the 2 points. Now, it has the point P, it has the point Q. That means the slope is the difference in the V coordinates divided by the difference of the U coordinates. So if the points are different, if the difference of the U coordinates is not 0, then that's the slope. And then we find a third point, let's call this R, and then take this point and compute the mirror image up there. This construction, draw one line through the points and then mirror it with respect to the x-axis. That is the addition of P plus Q. Then you might want to ask me, so what do you do for doublings? If P and Q move together, then, well, you see the slope changes from this, and eventually it becomes tangential to the curve. So if I do moving Q over to P, then the intersecting line becomes a tangent at the curve. So here is another curve, which is an example of having 3 real roots off the right-hand side, and here is a tangent in that point. Similar to the other case, I compute the other point of intersection. So I take the line with the tangent, find this point, mirror it, find the point here. Now, if you compute a tangent to a curve, then you take the curve equation and do, you compute the implicit differential. So you get the differential for x, so that's for u, so that's 3u squared minus 1, divided by the derivative for v, so that's 2v. So that's the slope of this curve. At this point, you should already notice that addition and doubling are quite different here. For the Edwards curve, I showed you, yes, it's faster to double. If I know that I'm doubling, I can specialize my formulas. I can bring it down from 10 to 4 multiplications, but I never had to worry that the additions would fail. If I accidentally would put in the same point here, I would have a division by 0. So for Weierstrass curves, it's really watch out if you have 2 points that you're adding, are these points the same or not? Also, I haven't showed you how I would add these 2 points, because then the slope would be, well, infinity, so it would be a vertical line, but I already put here a minus sign. So we'll define the negative of a point to be the point that you fit into the mirror image. So in general, I compute the addition by following this line, computing the intersection, so I'm solving the equation for the intersecting point, and then removing these coordinates. So I get the u coordinate looks like this, slope squared, where the slope was from addition or doubling, minus the u coordinates of the 2 points. And here I have the v coordinates of this. So if it's an addition with different u values, then the slope is the difference in the v values divided by the u values. If it's a doubling and we're not on this line, if we're not having v coordinate equals to 0, then that is the general equation of the slope. And otherwise, well, I said already, if we have the same u coordinate and the negative of the v coordinate, then we add those cases if they happen to be the same. So if we have this one, then the resulting point is something up here. So we need to pull out of the head an additional point which you can't see. We call this point infinity. You can imagine it's like infinitely high up there. So I can still do my pictures with always finding a third point on each line if I take that this line has these 2 points and 1 point high up there. So there's an extra point infinity, which we take as the neutral element. And so if I want to add 2 points, I have to check, is one of my input points this extra symbol? This is not an xy point. It's not a 2 coordinates thing. It's an extra point. So if I write a program, then I have to watch out, is it one of those special points or not? Next thing is, do I happen to add 2 points which have the same u coordinates? Then I cannot use this equation. If no, I can go ahead and do the addition. If they have the same u coordinates, then do I happen to double? Are these the same or are they of opposite sign? If I'm doubling, here's the formula. If I add 2 points like this, then I get infinity. So there's many more cases to consider. I said that Weierstrass curves and Edwards curves in principle are the same. So let me show you how I can move from one to the other. So this map is going to be something which is, well, a rational expression, so it has fractions of the coordinates, and I can go both ways. I'll show you how to move from the Edwards curve to the Weierstrass curve and how to go back. If you have such a map, that's called a birational equivalence. That means the curves are essentially the same. Anything you can do on one curve, you can do on the other curve. It even carries over, if you add 2 points here, get this point as a sum, you can either map the 2 points over and then add them, or you can take the sum and map that over. So it's a homomorphism. It fits with the group law. There are some exceptions, so if I write this out, then I get the u coordinates from the x and y coordinates like this. So you see that if y happens to be 1 or x happens to be 0, then this doesn't work, but it works for almost all points. So I move from the Edwards curve with these parameters to the Weierstrass curve with these parameters, where a is defined like this in terms of d, and b is defined like that. If I want to go back, then the x-coordinate, well, this was x, then I get the x-coordinate as a v divided by u, so it's easy, and also the y-coordinate I get like this. Again, there's some exceptional points, but it works for almost all of them. So you can go from any Edwards curve to a Weierstrass curve. What this means in terms of security is, if anybody would take an Edwards curve and you find an attack that works easier there, then you could also take the other people's Weierstrass curve and move over there. Or if you think it's more secure on it's easier on the Weierstrass curve, then, well, take the point on the Edwards curve and move it over to there. So whatever people have analyzed for the security of Weierstrass curves also holds for the security of Edwards curves. There's a little caveat because not every Weierstrass curve looks exactly like this. I might need to go to a quadratic or quartic extension field, but essentially it doesn't. If I have a polynomial time attack on one side, I have a polynomial time attack on the other side. There are maybe some constants which are faster on one side than the other, but you shouldn't have your security depend on a constant difference if you want to have, well, a real significant difference. However, if you're a designer of a system, you just need one good curve. So you pick a nice curve, you pick the curve which gives you the fastest group operations, and you use that thing. I haven't shown you the projective formulas for Weierstrass curves yet, but I can already advertise that Edwards curves are faster. So if you want to do fast arithmetic, then you stay on the Edwards curve. And you don't have to worry for doing new security analysis. Everything that has been done for Weierstrass curves holds here as well. So yeah, one last slide, and then we should maybe break for a few minutes. So the designer can choose where you want to do the computations, can do, well, in general, all you need is one good curve. So you can really specify one prime and one curve. So I said before, not every Weierstrass curve can be mapped to an Edwards curve. So sure, if you're bound to using, say, the standards by NIST, then unfortunately those don't fit with Edwards curves. But you only need one good curve, or maybe one good curve for each field size, for each security level. And so you can go ahead and choose this one curve to match with the nice properties. So I should also mention that what I showed you, this inversion-free thing, we call projective coordinates. I mean, projective coordinates has a mathematical meaning which happens to coincide with doing fractions and avoiding the inversions. So at this point, I suggest that we take questions for 5 minutes and then continue after the break.
So, you could take some questions if you have questions.
Ma'am, any device to understand that 256 ECC is a more faster than 3072 pitch RSA device?
So, so the reasons why the RSA is usually slower is that your modulus is many times longer. So if you take a 3000-bit modulus, it's more than 10 times as long as elliptic curve modulus. Then if you do a public key operation in RSA, then you have an exponentiation modulo this number. So whether it's a smart card or whether it's a PC, this exponentiation has a much larger modulus to deal with. Now, an elliptic curve addition takes 10 multiplications. An RSA multiplication, well, per bit just takes one multiplication, but it's a multiplication with a larger modulus. Now, with RSA, if you have, say, exponent 3, then that can still be faster. But then on the decryption side, you have a large exponent. If you have a slightly larger exponent than 3, elliptic curves also beats small exponent RSA. If you're on the smart card, then you'll have trouble implementing 3000 bits anyway. So I'm not sure whether this, I should be able to get online, but it might be easier. At the end of this, then we'll do some web page show. We have a benchmarking project called eBets for benchmarking public key cryptography, and there we have a huge range of different devices from low power ARMs and Cortexes up to high power CPUs like the latest K10 and such. And for each of them, we have implementations of elliptic curves, of RSA, of, well, hyperelliptic curves and whatever you have, and we show how fast they are. And at least for elliptic curves and for RSA, the picture is clear that elliptic curves beat RSA for a large range.
I want to ask you a question, whether elliptic curve are more efficient in software implementation with respect to hardware implementation?
Yeah, so this benchmarking project we have, that is looking at software implementations.
Okay.
So something where you're less restricted by your cache size. I mean, if you're doing hardware, then often enough you're on a very small hardware where even storing your 3000 bits runs into the problem, so you want to have a cryptographic coprocessor. Our benchmarking is purely looking at software implementations, and there we get the clear picture that also in software, ECC is much faster than RSA.
So, there is no more questions. Then you break for tea. We'll come back at 4:30. Then you are available for questions during the